Ideal and non-ideal solution. The main difference between these two types of solution. We will compare what are the features in which they are differing from each other. Okay. So here the interaction of A and B, that is the mixture of A component and B component, if we consider, they are forming ideal solution. So before forming the solution, there will be only AA type of interaction or BB type of interaction. And after mixing, there will be a new type of interaction which is between one A component and one B component. So this type of interaction, if it is just like AA interaction or BB interaction, so in that case, it will form ideal solution. But if it is not equal to AA or BB type of interaction, then there will be deviation from ideality. And the second important point is here del H mixing, it must be 0. There should not be any evolution of heat or absorption of heat. And del V mixing, that is also equal to 0. That means there should not be any volume change before mixing and after mixing. But in case of non-ideal solution, both these del H mixing and del B mixing, both are not equal to 0. Okay. And here, as it is following Raoult's law, so obviously partial pressure of component A, that will be equal to mole fraction of the component, that is XA, multiplied by P naught A. That is, when A component is in pure condition, in that case the corresponding vapor pressure, that is vapor pressure of pure A, that is P naught A. So PA will be equal to XA into P naught A. But in case of non-ideal solution, both these terms will be not equal to the mole fraction multiplied by the vapor pressure under pure state. Now, if we focus on non-ideal solution, it is not equal to 0, del B mixing also not equal to 0, then PA not equal to XA and P naught A. So when we are saying that it is not equal to, that means two situations may arise. One is it is greater than 0 or less than 0, or greater than XA P naught A or less than XA P naught A. So depending on two types of situation, under non-ideal solution, we can have positive deviation or negative deviation. So when it is positive deviation, obviously AB interaction is not equal to A and BB, but here the important point is this interaction is now weaker compared to AA and BB interaction. And here del H mixing is greater than 0, that means heat will be absorbed, and del V mixing is greater than 0. And all these are greater than, if we compare with the previous, that is ideal solution, now it is greater than XA P naught A and PB is greater than XB P naught B. And if it is negative deviation, this is opposite, that is now the interaction between A and B, it will be greater than the interaction of AA or BB. And del H mixing, that will be lesser than 0, and del V mixing, that is also less than 0. So here all these things are less than 0. So under non-ideal solution, there may be two types of deviation from ideal situation. One is positive deviation, another one is negative deviation. So if we know the value of del H or del V, just from the sign we can understand whether it is positive deviation or negative, because it will be positive, because greater than 0, del V mixing greater than 0, del H mixing greater than 0. Okay. And suppose if there is any numerical, so if we calculate this value, that is XA and P naught A, and calculate PA, if PA is greater than XA and P naught A, then obviously it will be positive deviation, and vice versa for negative deviation. Okay. Now in case of distillation, if we consider, we have already seen what is the theory of distillation. Now there is a term which is azeotrope. Now what is azeotrope? Azeotrope is actually that mixture which is also known as constant boiling mixture, where we are not able to separate the liquids from mixture to pure state. That is not possible. Now why it is not possible? Here also we will see deviation from ideality, but when it is deviated from ideality, depending on whether it is positive deviation or negative deviation, two types of azeotrope may be formed. So first you will see here we have deviation which is positive. So these two graphs are basically vapor pressure versus composition, that is mole fraction. So what is the difference between these two graphs? In the first case you can see that this is the ideal line, but actual vapor pressure is like this. But this is not very large deviation from ideal vapor pressure. There is a deviation, but it is minor deviation. And how to understand that whether it is minor deviation and major deviation? Just by looking at the picture, it may not be always possible to predict. So it is very easy to understand. And what is the criteria? Here the highest vapor pressure anywhere in this line. So what is the highest vapor pressure? This point. Now this point will never exceed the vapor pressure of pure component A or B. Here we have considered vapor pressure of A as if it is higher than vapor pressure of B arbitrarily. You can also consider the opposite. But here the important thing is the highest vapor pressure anywhere in the line. Obviously this is the point. It is still not greater than the vapor pressure of pure A. So the maximum point that will be actually equal to the vapor pressure of A. So if this type of cases are there, that means deviation is there but deviation is small. So we can consider it as if it is ideal mixture. As far as distillation is concerned, before we are doing distillation, we must be sure about the fact that whether it is possible to distill the liquid mixture from mixture to the pure state, and whether it is possible or not. If we want to know that, we have to know what is the corresponding vapor pressure composition diagram. So if there is minor deviation from ideality, it's okay, we can do the distillation, fine, it is almost like ideal. But if you look at the second picture, now the maximum point in the vapor pressure curve, that is exiting the vapor pressure of pure A. So now it is greater than the vapor pressure of A. So here the mixture have higher vapor pressure than either pure liquid. That is, whether you compare vapor pressure of A or B, from both these, obviously if we don't consider vapor pressure of B, it is fine because here vapor pressure of A is high. But the maximum point is even greater than the vapor pressure of pure. So if this type of situation arises, then we have to consider it as major deviation. So the maximum vapor pressure is no longer that of one of the pure liquid, as we have seen in the previous graph. So here maximum vapor pressure, that is matching with the vapor pressure of pure. But here that is not the case. This point is totally that is highly deviated from the maximum vapor pressure of any of these component. Okay, so this has important consequences on boiling point and distillation. So what will be the consequences, that you will see now in detail. Basically this, when there is major deviation, there is formation of azeotrope. But what is azeotrope, that we have to know, and we will do that by taking an example. Okay, now minimum boiling point azeotrope or positive deviation. So we have already seen in the previous graph that there is positive deviation. Okay, now if you look, that is at a first glance it may seem that this deviation is negative, but see, this is not vapor pressure composition curve, this is boiling point composition curve. So here we have basically temperature in the y-axis. In the previous curve there is vapor pressure in the y-axis and composition in the x. Here composition of x in x, but in x-axis, but temperature in y-axis, not vapor pressure. So don't be confused between the two curves, because these two are completely different curve. So in this picture, basically we are seeing that there is deviation like this. Okay, so we are calling it minimum boiling point azeotrope, and why the name is so, you will understand after some time. But remember, this type of graph for temperature versus composition we will get only when there is positive deviation. So positive deviation we observe when there is high vapor pressure. Okay, so high vapor pressure, then the ideal line. So just look at the previous graph. Here the actual vapor pressure is highly, that is positively deviated. That means the vapor pressure of the mixture is high. Now if the vapor pressure is high compared to the original pure liquid, then obviously the boiling point will be low. So that is why whenever there is positive deviation in the vapor pressure versus composition curve, and when you will switch to temperature versus mole fraction curve, there will be minimum temperature. So in this case, we have taken ethanol and water mixture. So ethanol and water mixture is actually the example of minimum boiling point azeotrope. So here, when vapor pressure is high, it means they will have low boiling point. Okay, so that is why the mixture is having low boiling point compared to the boiling point of pure water, which is 100 degree, and pure ethanol, which is 78.5 degree. Okay, so the minimum that we are getting, that is at 78.2 degree. Now you may think that this difference is so small, how does it matter? But actually it matters when we are doing the distillation. Okay, even if it is very small, still it matters. So the implication of this is that the boiling point composition curve will have minimum value which is lower than the boiling point of either component A or B. Okay, so this is 100 for pure water, this is 78.5 degrees centigrade for pure ethanol, and the minimum point that you are getting, that is lower than both of these values. So that is why it is minimum boiling point azeotrope. So when suppose we are starting from this line, that is now we have a composition which is more of water and less of ethanol. Now this is the liquid vapor pressure line for liquid, sorry, not vapor pressure line, that is a temperature line, this is for liquid. So when we will reach this temperature, now extend towards the right hand side. Now you are reaching the vapor composition curve, that is this is the temperature of the vapor pressure. At the same temperature, what is the composition of vapor? If we want to know, then we have to move in this direction. And now the composition of the vapor, because the purple line is for vapor, now the composition of vapor is C2. And when you are moving from C1 to C2, now we have, basically we are now moving from water towards mode of ethanol. So now in the vapor, the amount of ethanol will increase. Now at this point, if the vapor is cooled, then it will reach at C2. Now again if we move towards the corresponding vapor pressure composition, now we are reaching at C3. Now at C3 compared to C2, now the amount of ethanol is even higher. So in this way, again suppose you are moving here and another point, suppose C4. So ultimately when we will reach, suppose at this point, still it is the ethanol which is higher compared to water. But now the problem will arise because when we are reaching at this point, so at this point the composition is 95.6% ethanol and 100 minus 95.6 is for water. So this particular composition, when we reach, now see these two curves are meeting with each other. That means now the composition of this component A and B, that is ethanol and water, they are same, the same ratio of water and ethanol, both in liquid phase as well as in vapor phase. So we know that distillation is possible only when there is different composition of the two components in liquid phase and vapor phase. So until this point, you have seen that at the same temperature, just you can draw any temperature, at the same temperature it is always different composition for vapor and liquid. But when you are reaching at this composition, now that is at this composition of ethanol and water, that is 95.6% of ethanol and rest of it is water, now the composition is same. So that is why the two graphs are meeting with each other. So Now it will behave as if it is a new liquid having boiling point 78.2 degrees centigrade, because if you draw the line along this line, then it will be 78.2. So in case of mixture of ethanol and water, this minimum occurs with 95.6% by mass of ethanol in the mixture. So the boiling point of this azeotropic mixture is 78.2 degree compared with the boiling point pure ethanol at 78.5 or water at 100 degrees centigrade. So these two liquids are basically forming non-ideal solution, and we cannot separate them by fractional distillation. Okay, so if you are starting your distillation when the amount of ethanol is lesser than this percentage, that is, suppose any of this point, suppose you are starting, then what will happen when you will do the distillation? You will get the vapor which is gradually enriching with ethanol because you are shifting towards this side. But once you reach here, that is the end point. Now further you cannot pure it. So what you will get in the distillate? You will get in the distillate the vapor of ethanol. That means you will get liquid ethanol. And what will be remaining in the original distillation flask? There will be the mixture of ethanol and water, which is of 95.6%. Okay, and if you are starting from this point, that is, suppose here ethanol amount is 99% and water is 1%, or ethanol is 98, water is 2%, then what will happen? When you will start here the corresponding vapor, that will be, now we are moving towards this side, that means the corresponding vapor will have more of water because we are moving towards 100% water. So in this way, until this point it is fine, but once you will reach this point, now in the vapor phase there will be only ethanol. Okay, because there will be water because we are moving from right hand side to left hand side. So now the water will be in the distillate, and in the original flask there will be mixture of water and ethanol. Okay, so this is the example of minimum boiling point azeotrope, and next we will see what is maximum boiling point azeotrope. Now for maximum boiling point azeotrope, which is basically negative deviation. So negative deviation means, just remember the vapor pressure composition curve, because this curve is temperature versus composition, but negative deviation, that is for vapor pressure composition curve, vapor pressure versus mole fraction. So if a mixture has lower vapor pressure, that means negative deviation in the vapor pressure composition curve. That means obviously it will have higher boiling point, because lower is the vapor pressure, higher is the boiling point. It is inverse. So that is why now the azeotrope that we will get, that will have maximum boiling point. So this graph you can see, it is just opposite that we have seen in the previous slide. Fine. So here the example that we have taken, that is the mixture of HNO3 and water, nitric acid and water. So in the left hand side we have 100% water, that is pure water, temperature 100 degrees centigrade, and in the right hand side we have 100% nitric acid having boiling point 86 degrees centigrade. Okay, and suppose we are moving from this line, so when we are here, that means more of water and less of nitric acid. Now when we are reaching at this point, the corresponding point in the vapor pressure is this. So this vapor pressure, when we are reaching, I have done wrong, we have to start from this point, not this one. So when we are starting from C1, we are reaching at this point, and then at the same temperature, if you move towards left hand side, you will reach the vapor pressure composition. Now if this vapor is condensed, then what we are getting? Now we are reaching this mole fraction. So compared to the point C1, now suppose if it is C2, Obviously in C2 there is more of water and less of nitric acid. Okay, so that means if you are starting before this composition, so this composition is basically where the maximum is appearing in the curve. This is 68% nitric acid. So if you are taking any point here, that is 56% nitric acid or 50% nitric acid, then always in the vapor, as you will be moving towards this side, always in the vapor there will be more of water and less of nitric acid. Similarly, if you are moving from this side, any of this point, so in this in the right hand side of 68% nitric acid means that there will be 90% nitric acid, 10% water, or 95% nitric acid, 5% water. So what will happen? Suppose we are starting from here, this is the point, and if we take the corresponding vapor pressure curve, suppose this is the point, so gradually what will happen? The amount of nitric acid will increase, because as we are moving towards this side, the amount of nitric acid will increase. So basically in the distillate means in the vapor, suppose we are moving from this line, we are reaching at this point, at the same temperature if you move towards vapor, this will be the vapor composition. Now in the vapor composition the amount of nitric acid is high. So that is why if we are starting from higher percentage than 68, then in the distillate we will always get pure nitric acid. But that does not mean we can purify the two liquid, because ultimately we cannot do so, because once we reach this composition, then we will get only, that is the liquid which will be behaving as if it is a pure liquid. So it will form a liquid that is a mixture of nitric acid and water, which is 68%. It will behave as if it is a new liquid having boiling point that is 120.5 degrees centigrade. So the implication of this is that the boiling point composition curve, now it will have maximum value higher than the boiling point of either A or B, that is the boiling point of water or nitric acid. From both this value, now the value of 120 degree it is high. In the case of mixture of nitric acid and water, there is maximum occurs at 68% mass of nitric acid, and the boiling point of the mixture is 120.5 degrees centigrade. Okay, so which is higher than these two. So these two liquids are also forming non-ideal solution, and we cannot separate them by fractional distillation, because once we reach at 68% of nitric acid, whether we are moving from this left hand side or right hand side, that is we are moving from more of water side or more of nitric acid side, once we will reach at this point, we cannot move further, because at this point the composition of A and B both in liquid and vapor are same. But the criteria for distillation is that the composition of the two component must be different in the liquid and vapor phase. But if it is same, we cannot distill it. So that is why here fractional distillation is not possible. And this is the example of maximum boiling point azeotrope, which is possible in case of negative deviation in vapor pressure composition curve. So now we will summarize the result. For the first example, that is ethanol and water, which is basically arising because of positive deviation, so that is why the boiling point is minimum. So if you are starting distilling ethanol water mixture which is containing lesser than 95.6% of ethanol by mass, then it will give us the opportunity to collect a distillate containing 95.6% of ethanol in the collecting flux. That means where we are collecting the vapor after condensation. But it is also important to mention that provided we are careful enough with the temperature control and the fractionating column is long enough, otherwise we cannot expect this result. Okay, and there will be remaining pure water in the distillation flux. Okay, Next possibility is if you are distilling ethanol water mixture containing more of 95% 0.6% ethanol. That means suppose we have 99% ethanol, 1% water. So if we start from that, what will happen? We will get a distillate which is 95.6% of ethanol. That is, we will get azeotrope in the distillate, and in the collecting flux there will be pure ethanol, that is in the distillation flux. And what about the maximum boiling point azeotrope? In case of maximum boiling point azeotrope, if we are starting lesser than 68% by mass of nitric acid, that means suppose 50% nitric acid, less 50% water. So in that case, what will happen? Water as distillate in the collecting flux and 68% nitric acid, that is the azeotropic mixture, that will be remaining in the original distillation flux. And if we are starting with a nitric acid water mixture where amount of nitric acid is greater than 68%, in that case, in the distillate there will be pure nitric acid, and in the distillation flux, that is the flux from where we have started the distillation process, there we will be left with the azeotropic mixture. Colligative properties, the properties of dilute solution. So these properties are observed in case of dilute solution, and that depends only on the number of solute particles. So here what type of solute you have taken, that is not important, but what is the number of particles of the solute present in the solution, that is important. So the identity of solute is not important. So these type of properties are known as colligative properties. Now colligative properties, under these properties we will discuss total 4 types, which is elevation of boiling point, lowering of vapor pressure, depression of freezing point, and osmotic pressure. And remember, these colligative properties, they are related to each other. The vapor pressure of solution, we know that it decreases when we are adding some non-volatile solute to the volatile solvent. So there is a mixture of solid and liquid. The liquid is solvent, which is volatile, and the solute is solid, which is non-volatile. Okay, so there are many properties of the solution which are connected with this observation. Which observation? The first point, that is the vapor pressure decreases when there is non-volatile solute. Okay, now this lowering of vapor pressure, it has several consequences. Fine. So many properties of the solution basically connected with this lowering of vapor pressure. So colligative properties, remember, it is only for dilute solution that are supposed to behave as ideal solution, because if it is not behaving as ideal solution, the whole discussion is meaningless. Okay, so it is only for dilute solution, and remember they are related to each other. So when we will discuss further, it will be clear how they are related to each other. And remember, here the solute that we have taken, it should not dissociate or associate in the solution. So suppose you have taken any electrolyte, KCl, so it will be dissociating as K plus and Cl minus. But suppose you have taken glucose, it will not dissociate because it is not electrolyte. So in the first case, as we have said that here nature is not important, but the number of particles is important. So when from a single particle, suppose KCl, now you are getting K plus and Cl minus. So here it is only one particle, but here we are getting 2 particles. So obviously now the result will vary. But in case of glucose, when there is no dissociation, then particle number will be same, whether it is in solution or in solid state. So that is why it is important to you have to be very careful about the type of the solute that you have taken, because when you have taken electrolyte like KCl or any other electrolyte, we cannot expect the behavior as if it is acting as one particle, because when it is in the solution, mostly it is aqueous solution, then it will behave as if it is per particle there is actually 2 particles. So these properties, when we will discuss, we will see that this must be mentioned. This must be, we have to take care of this fact, whether there is dissociation or association. Association means suppose there is any solute, suppose you have taken A, and when you are adding it to solution, suppose 2A molecules now as if it is behaving as A2. So what will happen? Here the colligative properties will differ a lot, because here it is 2 particles but here it is behaving as if it is 1 particle. So this is actually association, and the first example is dissociation. So these two, this type of process should not be there, otherwise there will be error. But we will also see that after discussion of all these 4 types of colligative properties, that when there is this type of cases, that is suppose there is any association or dissociation, then what we will do? So under when this type of situation will arise, there is a different process by which we can find the colligative properties. But we have to know what is the nature of the solute, whether there is any chance of dissociation or association or not, because accordingly we will consider what is the total number of particles, whether it is 1 or 2 or 3. Okay, because it is very simple, that is KCl you are getting just 2, but maybe there is any formula, suppose of the salt is A2B3, then you will get 2A plus cation and 3B minus anion. Okay, basically it will be having oxidation state plus 3, it will be minus 2, so that is plus 6 charge and minus 6 charge. So you will get 2A ion, A cation and 3B anion. So see, from 1A to B3 you are getting 5 particles. So obviously as it is colligative property, it will have a huge effect, because now the number of particles increased from 1 to 5. Okay, so we'll start from lowering of vapor pressure, which is the first colligative property. So we already know that when a non-volatile solute is dissolved in a liquid, the vapor pressure of the solution, now it is lower than the vapor pressure of pure solvent. And from Raoult's law we know that the partial vapor pressure of any component in the solution is directly proportional to the mole fraction. So if there is component A and B, then PA will be now equal to XA of P naught A. So XA is basically always less than 1, because it is fraction, it is mole fraction. So obviously PA, it will always be lesser than PA naught, because now with PA naught you are multiplying some fraction. So obviously the value of PA will be lesser than P naught A, or PB is lesser than P naught A. Okay, now here in the picture we have volatile solvent particles, which are the blue particles. So this is actually pure solvent, there is no solute. But when you are adding some non-volatile solute, that is these red particles, now red particles are also there. So if you look at the surface, in the previous case when it is pure, there is only the blue particles, but now in the surface, actually why I am focusing on surface, because only from the surface they are going to the vapor phase. Okay, so there is some equilibrium, they are moving, they are coming towards liquid and they are moving towards vapor. But when there is some solute particles present, in the surface number of blue particles, that is the solvent particles, that will decrease. So the rate of vaporization, that will be reduced by the presence of non-volatile solute. And after that one time will reach when equilibrium will be established with fewer molecules in the gas phase. So here the total number of blue particles that we are seeing in the vapor phase, here the number of particles are lesser, that is clear from the picture. Okay, so now the solute particles are, the solvent particles, they are in fewer number in the gaseous phase. Now suppose we have dissolved small n moles of non-volatile solute and capital N moles of volatile solvent. So small n for solute and capital N for solvent. So the mole fraction of the solvent will be, that is x1, or you can say xa, whatever it is, of the solvent will be capital N divided by the total number of moles of solvent and solute. Similarly, the mole fraction of solute, it will be the number of moles of solute divided by the total number of moles. Now since the solute is non-volatile, so it will not be in vapor phase. It will have negligible vapor pressure because it is not volatile, so it will not be in vapor phase. So the vapor pressure of the solution, it is only because of the vapor pressure of the solvent. And according to Raoult's law, the vapor pressure of a solvent in an ideal solution, it will be given by this expression. So now 1 means solvent. This 1 signifies solvent. X1 is the mole fraction of solvent. Okay. Now from this equation 1, what we'll do, in place of X1, you can put this value, right? So this is equation 1, and P1 naught is the vapor pressure of the pure solvent. That is before we have made the solution, when it is in pure condition. And mole fraction are always 1. So now we can write in place of X1, we can write this, that is 1 minus X2. So basically what we are doing, we are expressing the vapor pressure of solvent in terms of mole fraction of solute. Okay. So now P1 by P1 naught, that will be 1 minus X2, or ultimately we can get this equation. Now this equation is very important. This is the mole fraction of solute, and this is the difference of the vapor pressure before and after. So before it was pure solvent, then the vapor pressure is P1 naught, and after making solution it will be P1, and P1 is lesser than P1 naught, so that is why P1 minus P1 naught minus P1 divided by the original vapor pressure. So this ratio, that is, I am talking about this ratio, this is known as relative lowering of vapor pressure. So why it is relative lowering of vapor pressure is this numerator, but when we are saying relative lowering, that means compared to the initial vapor pressure, what is the lowering? That is why it is relative lowering, and this is equal to X2, that we have already proved. Now you can write in place of X2. In the previous slide we have seen that it is actually n by n plus n, small n and capital N is there, or directly you can put in place of X1 the expression for X1. Okay, so when you will solve numericals depending on the requirement, you can use any of this equation, but once you know this equation and this X1 plus X2 equal to 1, you can easily write any of these. So you don't have to memorize any of these things. If you can do so, it is fine, but just remembering these two is enough. Okay, so equation 3, we can state it as relative lowering of vapor pressure of a solution which contains non-volatile solute, that will be equal to the mole fraction of the solute present in the solution. So this is the mole fraction of the solute present in the solution. Okay, so this equation is very important, and as I have said that we can write in place of X2 this ratio, because this is actually the mole fraction. So from equation 4, what we can say, that lowering of vapor pressure of a solution, it depends upon the number of moles of solute and not upon the nature of the solute. Okay, so here it is simply the number, there is nothing any expression which is related to the nature of the solute. Okay, so that is why it is colligative property. So we can now say that lowering of vapor pressure, it is a colligative property, because in the final expression there is no expression which is related to the nature of the solute. Okay, so now we will solve a problem regarding this relative lowering of vapor pressure. So the idea about it will be more clear. So here we have the problem. The vapor pressure of a solvent decreased by 10 millimeter of Hg. That means the difference between the original vapor pressure and the new vapor pressure, that difference is 10 millimeter of Hg. When a non-volatile solute was added to the solvent, obviously that will be the case, that is lowering will take place. Now the mole fraction of the solute in the solution is given, which is 0.2. What is the mole fraction of solvent? That we have to find out if the decrease in vapor pressure 20 millimeter Hg. So first it is mentioned 10 millimeter Hg when the mole fraction of solute is 0.2. But you have to find mole fraction of solvent not in this case. You have to find it when the decrease in vapor pressure is 20 millimeter of Hg. Okay, so all these are options. Obviously there will be no unit because it is mole fraction, so no question of unit. Okay, so here we will write the expression that we have seen in the previous slide. P1 naught. So P1 naught, it is for pure solvent and this is for solution, and that is equal to x2. Now x2 is given the value 0.2 and this is actually, you can write it as del P. So del P is also given, which is 10. So from this equation we can find the value of P1 naught. So P1 naught will be 10 by 0.2. So it is 50 millimeter Hg. Again we will write the same expression, that is P1 naught minus P1 by P1 naught. Now this mole fraction x2. Okay, what should be the mole fraction of the solvent, that we have to find out. So x2 we can find out how, because we know the difference, that is 20 millimeter Hg. So in place of numerator we will write 20 and P1 naught we have already calculated, which is 50. So this ratio is 2 by 5, which is basically 0.4. So x2 is 0.4, but we need the value of x1, not x2, and we know that x1 plus x2 is 1. So x1 will be 1 minus x2, that means 1 minus 0.4, 0.6. So the answer is 0.6, that is option B. Fine. Another problem. What weight of solute molecular weight is given, which is 60. Now what weight of the solute is required to dissolve in 180 gram of water? So this is solvent. To reduce the vapor pressure to 4 by 5th of pure water. So exact value is not given, but if pure water vapor pressure, if you consider P naught, then the reduced, that is after making the solution, the vapor pressure that will be reduced, that will be 4/5 of the original amount. Okay, so first here what we'll do, we'll find out the mole fraction of solute, that is x2, and we know to find x2 we have to find out small n and capital N, or you can consider n1 and n2. So suppose moles of solute suppose it is n2, that will be equal to the weight that we actually do not know. Suppose the weight is W, because that we have to find out what weight of solute, divided by its molecular weight. Similarly, moles of solvent N1, that is, now here the given mass of solvent is 180 and molecular weight of water 18, so this will be 10. Okay, so now we can write the expression for x2, which is N2 divided by N1 plus N2, and here relative lowering of vapor pressure, that is P naught. Suppose this is for solvent, you can also write 1 P1 naught, that is equal to x2 or N2 by N1 plus N2. Now relative lowering of, that is the new pressure generated after making the solution P1, that is 4/5 of the original. So we can write in place of P1, it is 4 by 5 of P1 naught divided by P1 naught, and this is equal to, in place of N2 we will write W by 60, then W by 60 plus 10. Okay, so from this we can write, in the left hand side it will be 1 by 5 P1 naught divided by P1 naught, so this will be cancelled by 60. Or we can write 1 by 5 W by 60 plus 10 by 60. Okay. So here 1 by 5, that is W by 16 plus 10, that will be equal to W by 12. That is 5 we are taking in the right hand side. So 10 is equal to basically W by 12, W by 60. Okay, so this is actually 4W equal to 600, so W will be equal to 150. So this is the weight of solute that is required, that is 150 gram of solute we will dissolve in 180 gram of water, and if we do so, then the relative lowering of vapor pressure, that will be this term, that is the new vapor pressure that will be generated for solution. This is for solution, that will be 4/5 of the original value. So exact value is not given because we are taking ratio, so original value is not required. Okay, P1, because ultimately P1 not it is cancelled. So the amount of solute required is 150 gram. So the first colligative property we have discussed, lowering of vapor pressure. The second one is elevation of boiling point. So basically this lowering of vapor pressure is actually the cause of the rest of the three colligative properties, you can say. Okay, so because there is decrease in the vapor pressure after addition of non-volatile solute, so that is the reason for the elevation of boiling point. So you can say that this is the consequence and the cause is the lowering of vapor pressure. Fine. So here the boiling point, what is the definition of boiling point of a liquid, that we have to know. So this is the temperature at which the vapor pressure becomes equal to atmospheric pressure. That is the vapor pressure of the liquid that becomes equal to the atmospheric pressure. Then only it can boil. And atmospheric pressure is basically 760 millimeter or 1 atmosphere. So in this picture we have taken vapor pressure in the y-axis and temperature in the x-axis. Okay, and in the vapor pressure axis this point is for atmospheric pressure, and at first we have pure solvent. So this is the graph, this is the line for, that is the AB line, that is for solvent. Okay, so solvent, when you are increasing the temperature, you are moving towards this side, gradually you will reach one point which is TB naught. So at TB naught temperature, this line AB, it is meeting with this particular atmospheric pressure point, that is this point it is meeting. That means at this point, that is the corresponding temperature TB naught, at this point it will start to boil. So this is for solvent. Okay, and since the vapor pressure of solution is always lower than that of pure, so when it is solution, that is now you have to consider the line CD. So you can see this line is just below the line of AB, because now there is lowering of vapor pressure. Now it is solution, it is no longer pure solvent. So because of this relative lowering of vapor pressure, the solution must be heated to a higher temperature so that we can make the vapor pressure equal to atmospheric pressure. Now as you extend the line, if you suppose now you have reached the boiling point, but if you draw a corresponding line on the vapor pressure axis, this vapor pressure is lesser than 760, so it cannot boil according to the definition of boiling point. So that means now you have to move further towards right hand side. So from TB naught, now you have to increase the temperature up to TB, and at the point TB, now the line CD is meeting this point 760 millimeter. So now boiling is possible. That means TB here is greater than TB naught. TB is greater than TB naught. So that is why it is elevation of boiling point. So now the solution, it will boil at high temperature compared to pure solvent. So here we will consider TB naught is the boiling point of the original solvent, pure. TB is the boiling point of the solution. So if you take the difference, that will be del TB, and that del TB is actually the elevation of boiling point. Okay. So if in numerical it is mentioned that elevation of boiling point is 0.4 degrees centigrade. So that means del TB value is 0.4 degrees centigrade. Okay. So del TB, that is actually proportional to molality. But if we remove the in proportionality sign, there will be a constant which is Kb. Now Kb, it has a name, it is molal elevation constant or ebullioscopy constant. Okay. So this M is basically molality, not molarity. Be very careful. It is molality, because if you consider molarity, when you will solve numeric, it will be wrong. Okay. And see here the unit of Kb, that is Kelvin kg per mole. Now in the left hand side the unit is Kelvin because it is temperature, and for molality the unit is moles per kg. So the unit of Kb, it must be Kelvin because in the left hand side we have Kelvin, and the reverse unit of molality, that is now it is kg per mole, not moles per kg. Okay. So we can also find the unit in this way. Sometimes it may happen that Kb value will be given, you have to find molality. That is any of these among these three, if two are given, then you can find Kb. And it may be that sometimes directly molality will not be given in the numerical, but instead of molality, suppose the weight of solvent or solute will be given and the molecular weight. So we can easily calculate the molality, and then we will put in place of small m the molality value, and we can find the unknown del TB or Kb. Okay. And if del TB and Kb is known, then also we can find the molality. And once we find the molality, and if the weight of solute is given, we can easily find the molecular weight of solute. So from this expression, basically we can also find the molecular weight of solute. Okay, provided that is amount of solute is given. So you know the number of moles, you know the amount of solid given, so you can easily find out molecular weight of solute, because given mass by molecular weight is equal to number of moles. So if you know the number of moles and given weight, you can find molecular weight. Okay, so that is the importance of this expression, del TB equal to Kb into molality. So regarding this expression, here we have a problem. 10 gram of solute, solute molar mass is given 100 gram per mole, and we are dissolving it in 100 gram solvent, and it is showing 0.3 degrees centigrade elevation in boiling point. So what we have to find out? The value of molar elevation constant, that means we have to find out Kb. So here the expression del TB is equal to Kb into molality. Fine. So del TB is given 0.3. Kb we have to find out, this is unknown, and molality directly not given, but we can easily calculate it. So 10 gram of solute, that is the given weight of solute, and molecular weight of solute is given. So number of moles of solute, that will be equal to given mass, that is 10 gram, divided by molecular weight, that is 100. So this is 0.1. Now this number of moles, that is present in 100 gram. So we can write that 100 gram contains 100 gram solvent. It contains 0.1 mole of solute. But we require molality. So for molality, according to the definition of molality, the number of moles of solute present in 1000 gram solvent. So 100 gram solvent contains 0.1. So 1000 gram solvent will contain simply 1 mole. Okay, that is 10 times high. So now this is actually the molality. So we can write here 0.3 kb into 1. So basically kb is equal to 0.3. And what will be the unit? Though here unit in the options are not given, it will be kg per mole. Fine. So correct option is option C, that is 0.3. Okay. The third colligative property, which is depression of freezing point. So first one is lowering of vapor pressure, that is the relative lowering of vapor pressure, which is equal to mole fraction of solute. The second one is elevation of boiling point in the solution. And now depression in freezing point. So when it is boiling point, there is basically increase, that is compared to solution, compared to pure solvent. In case of solution, boiling point is high, but now it is opposite. When you are considering freezing point, now it will be lesser than the freezing point of pure solvent. Okay. So what is freezing point? You know what is the definition of boiling point. Similarly, the freezing point of a substance is that temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure in the solid state. So similar type of definition that we have seen in case of boiling point, only now we have vapor pressure of liquid and vapor pressure in the solid phase. Okay. So here in the graph, we have taken vapor pressure in the y-axis and temperature in Kelvin in the x-axis. So this is frozen solvent, that means this is solid solvent. Frozen solvent means solid solvent. So this is the line for vapor pressure of frozen solvent, the black line. And for liquid pure solvent, this is actually pure solvent. So solvent can remain in two states, that is liquid solvent, and as you are decreasing temperature, it will be solid solvent, that is frozen solvent. So these two lines are meeting at this point. That means, according to the definition, when the vapor pressure of the substance in its liquid form phase is equal to the vapor pressure of solid phase, that means if you draw a line from this point on temperature axis, this is TF naught. So this is the freezing point of pure solvent, because at this point it is meeting this is the point of meeting of these two vapor pressure line. Now, so when you are adding non-volatile solid to the solvent, vapor pressure will decrease. So that is why now the line for solution, which is this blue line, this line is lower than the orange line, because orange line is for liquid solvent which is pure. So now vapor pressure will decrease and it will become equal to the solid solvent at lower temperature. So now the meeting point is somewhere here. Now if you draw line corresponding that is which is falling on the x-axis, you are getting a temperature TF which is lesser than TF naught. So TF is lesser than TF naught. So this is for pure solvent, this is for solution. Okay. So from the graph, it is very clear that when we are adding solute, now the freezing point will decrease. Okay. So here TF naught is the freezing point of the solvent and TF is the freezing point of the solution. This is the difference, just like del TF we have seen in case of elevation of boiling point. So del TF will be depression of freezing point. And for dilute solution, that is ideal solution, it is directly proportional to M. So just TB is directly proportional to M, del TF is also directly proportional to M. And if we are removing this proportionality sign, there will be a constant which is now Kf. So in case of boiling point, it is Kb, B for boiling, and now it is F, F for freezing. And Kf is known as molar freezing point depression constant, or it is also known as cryoscopic constant. M is molality and the unit of Kf, just like before, it is Kelvin kg per mole. Okay, sorry, it is L. So that is all about the depression of freezing point. So when we will solve numericals on related to depression of freezing point, the idea will be more clear.